So after my augmentation task, the thing that I need to do here right now is creating the binary masking using the OpenCV library. So for doing that, what I have done here is, again, first I have imported the libraries and the glob function, or the glob library basically. What I have already explained that glob is used for traversing around the files. Then I have created the image mask, then the mask directory, image directory, created a function. Now from the image path I had created an output directory, so that the images, when the images enter inside my function, and when it exits from my function, the all the images along with their individual binary mask will go inside the output directory. And so I have used the, first I have loaded the images in the cv2.imageread, converted the color to BGR to HSV, and then using numpy arrays, I have defined the red color range in HSV, which is nearly equal to 0, 40, 40 for the lower red, upper red is 50, 20 to 25, 16, 40, 40 for lower red 2, and upper red 2 is 180, 250, 255. So it is a lower bound in the upper bound by which the OpenCV library will define the range of the red color inside the images. And when the red images are identified, it will try to bitwise the images from mask 1 and mask 2. And the blur, or the masking that I am using here basically for the red mask is Gaussian blur. Gaussian blur with the red mark of 5 by 5, 0. And kernel are the NP1s. NP1 means the area whenever the mask is present will be binarized as zeros, and the other areas will be binarized as 1. and then I use the function of cv.dilate. Okay. These are the weights that I created as center mask weighting and blend red mask weighting, and threshold I created here with the ranges that I have defined earlier. And once the mask is created, then I have to save the mask. I am using the os.path.base name and the image path, and I have replaced it with .png with mask.png. So whichever dataset images will have the name with mask.png, it will identify as the masked images. So center focused mask has been generated and been created inside the PNG file augmented masks. Okay, so these are the original image, and this is a generated mask that I have got through the OpenCV library. As we can see, it's quite precise. I would not say completely accurate, but it's quite precise, since I've used already data augmentation for making it cropping and then resizing the images. Okay, after the masks are generated, then I need to again split a data set with the respect to masks, trained mask paths, valid mask paths, and test mask paths. The same thing that I have done earlier with the splitting, the same thing I am doing here with the mask as well. 50,330 for the trained mask, 43270 for valid mask, and test mask is 2300. So now the total number of this is a checker function that I created, so that I can identify whether any of the files have created a mask or not. Because if any one of the file will not have a binary mask created with its associated with itself, then it might default during my unit segmentation task and will not perform the operation. So after doing that, I have created the visualize function for reading the files, and I am showing how these images are looking. Generated masks, these are all the generated masks without any of the images being not masked. Now in this section, what I am doing here is before defining the architecture of unit, or customizing the unit architecture with the autoencoder, decoder, and the skip functions, I have created the class segmentation dataset here for channelizing all the masks that will be as the input for the architecture, and so that with the transforms for the PyTorch framework, so that there is no workflow default inside the architecture. This is the whole transformation that I have done earlier for the original dataset, and I am doing this again for the masking as well. So this after applying those train image transform functions, what this does is I'm using the compose, resize, horizontal flip, vertical flip, tensor, normalize, resize, these all functions with mean and standard variation for the train image and validation image itself. Because these are not done for the test images, since the training image and the validation image are enough for providing data set of how to telling the data set how to perform the binary masking on the predict the binary masking inside the original image. And if I provide that with the test data set itself, it would not be beneficial, since it would already have all the values inside it, and the result will be 100%. So I cannot show it for the test data set. Same I have done for train mask transforms. Okay, so now it is very important for us to load the data set for the unit architecture. And for loading, I have used the batch size here for 4 for the train loader. Validation loader, what I have changed here is I kept the batch size 4, but I have not used shuffle equals to false. What this does is basically all the images that will be there in the validation loader, it will automatically be aligned in a particular sections, so that the unit architecture during its bottleneck structure will be easily able to train itself and verify whether the accuracy was correct or not. This is done for reducing the training time. So these are the number of batches for test loader and test dataset. These are the batches that I have created here. This is the batch for the data loader. I have used the in this section I have used the squeeze function for that, so that any of the images with extra dimensions are identified as null, because all the images are needed to be transferred to dot to tensor for the GPUs to compute the values. And now this is the architecture that I have used for the custom unit that I have taken from 2015 paper from Leonard work. This is the unit architecture here. This is the class unit, and this is a definition unit that I have created, with the encoder block. This is the encoder block. This is the bottleneck, and this is the convolution normalization. I have used the leaky ReLU activation function. Leaky ReLU activation function I have used here because it's a bit more modified and up-to-date function rather than just using the ReLU function. I have also used dropout function here. Dropout function help us for the regularization purpose and generalization of the data set, so that my output images are not output results are not overfitted. This is the decoder block. From the image you can see that this is the encoder block, this is the decoder block, this is the bottleneck. I have also mentioned the maths inside that at the end of section that I can show. This is the convolution block, this is the convolution block, this is the forward. Forward functions are used for defining the neural networks for the feed forward propagation and back propagation, so that all the max pooling, stacking, padding takes place very efficiently. So this is the class instance that I have saved to 2 devices with the GPU. Device here is GPU CUDA, and the TOS size here is 256. The optimizer that I used here is TOS.optimode Adam optimizer with a learning rate of 10 to the power minus 4. I have tested many learning rates from ranging from 0.1 to 10 to the power minus 4, but the most accurate or the best result with the hyperparameter tuning is with IE minus 4. And the scheduler that I have used is TOS.optimode LR scheduler. LR scheduler helps, what this does is the learning rate sequentially grows itself with the plateauness from this reduce LR on plateau function. This is done optimizingly with each epochs increasing with a patience level of 5 and factor equals to 0.5. I have also used the TQDM with TQDM input function for showing everything with the progress bar. Then for calculating the accuracy matrix used for the unit architecture is dice loss, the BC loss, and the IOU scores. So I have defined here the dice loss with this function, the forward propagation for this, and the sigmoid activation function for converting the logits to probabilities. They targeted each dice with this formula, and this is the IOU score. The IOU score also I'll explain at the last how this works as part of the mathematics section. This is the combined loss with IOU, the BC loss, and this is the BC with logit loss. So the binary cross entropy, since we are using here binary masking, so binary cross entropy plus dice plus IU score is used here for the whole accuracy matrix. This is the training loop that I created with the train loader, val loader, optimizer, number of epochs, device, patience, and then all the values that I have kept here. I can show it. Validation phase. This is step scheduler for the learning rate inside the validation loop. This is the function that I have created for saving the model, the best model for the unit architecture wherever it finds. And I've used the early stopping counter. What this early stopping counter does is whenever the accuracy with the next loop is not a big difference, it will identify itself with a patience level of 1, 2, 3, 4 up to a level of 5 or up to a level of 3, whatever I can define. So after reaching that limit, it will just stop the counter and end the whole training loop, saying that the accuracies are not increasing. So this is the instance of the whole training loop, and this is the model. I am calling the model with the unit in channel 3, out channel 1, because since the out channel should be 1 with the generated predicted mask, and this is the device agnostic code. This is the learning rate, and this is the model calling with the number of epochs equals to 20, patience equals to 5. So as we can see, the whole set I've shown with the progress bar, and total number of epochs that I had ran to is 12 out of 20. It ran till 12. Since after that the patience level has already crossed its limit, and the model training loop just stopped. As we can see that the best model was saved in the third one with validation loss of 0.1318. We will get to know what is the training loss and validation loss at the end. So dice coefficient and IO score calculation, this is the function for that after once the whole training loss and validation loss are stored. This is the testing loop where I have created the dice coefficient and I calculated every value for whatever the predicted mass generation, evaluating model, and so on. So after evaluation of the model with 1068 images from the test data set, the dice coefficient that I received was 0.8132 and final IU score was 0.794. The standard unit architecture which I can use for transfer learning could have given me a more better result, but the architecture that I have used here is giving me a finer result than that as well. So after doing those work, I'm showing the segmentation outputs of the model predictions. This is the original image that I had taken. This is the ground truth mask, and this is the predicted mask by the model unit architecture. This is the original image. This was the ground truth mask. This was the predicted mask. As we can see, these are not the accurate one because here in this region there is no red hue or the red color that has been found. So it is not able to detect where the red color was. In this case, we can see it was pretty much similar, and so the dice coefficient here was very high. Similarly, predicted mask and the original mask are very common together. And in that way, I have stored the trained model inside my Google Drive itself in the Collab notebook with the model evaluation and model 2 device for the GPU. This is the whole architecture that I had used. So after the training evaluation is done, for the testing of the data for the model, I have created a testing loop This is a testing loop. This is the no grad function with the forward pass, calculate matrix, average matrix, as earlier that I had used earlier. Same thing with 2300 images for the testing file, and the dice coefficient I received here is 0.8116 and test IU score is 0.7534 for the best model. Now I'll show with the test images how my model predicted. That as you can see in the original image, the ground truth mass was very fair, but the predicted image wasn't able to show a very good result inside. In the original image, the ground truth mass was very fair, but here also it was not able to show, since the images here was a bit blurred out with the yellow color. But in this case, the reddish areas are very clear, and so it also generated the same similar type of binary mask. Here also the reddish area were very clear, so it was able to generate the binary mask. So the unit architecture, I have already explained the encoder, decoder, the input imaging, convolution, pooling layers, upsampling and everything. And at the end, the thing that I had introduced here was the upsampling with concat from skip connection. What skip connection does basically, it only focuses on those blocks of the function where the features are more likely to give more better results, like the attention block. It is a pre-attention block module that I have used here. And finally, I have presented the whole mathematics, how the dice coefficient and ISO score works. So this is my complete project regarding the SIC AI. I hope everyone finds it well. Thank you.